I can give you a Lego model and say, take it apart and build it back. And you might get it close, but it's probably not going to be exactly the same model that I gave you. And now you do that 100, 500, 1,000 times. By the end of it, you're going to get something completely different. And zinc electrodes are a lot like that.
Welcome to Battery Generation, your electromobility podcast for European battery research. Dear listeners, if you like what you hear, hit the subscribe button and help the algorithm find us. We're talking to a great guest today. It is Dr. Simon Clark. Hello.
Hi, thank you for having me.
You are a senior research scientist, a battery model developer, and a data scientist working at SINTEF in Norway, one of Europe's largest independent research organizations.
Simon, we are talking about one of your battery expert fields today, about Zinc-Air batteries. We're focusing a lot on lithium-ion batteries in this podcast, but one might really underestimate the cell chemistry of Zinc-Air batteries. First question for me, where can we see these zinc or Zinc-Air batteries as of today?
One of the easiest places is to just go down to your neighborhood store, where you'll often see them on the rack right next to the checkout, usually called something like hearing aid batteries. That's a good point. That is a zinc battery, but that's an alkaline battery. Zinc-Air batteries, you can actually tell it's easy to identify them because I have one here with me, and they always have this special little bit of plastic on the top, this little blue label. And that's actually because one of the active materials in zinc isn't in the battery itself, but it comes from the air. It uses oxygen from the surrounding air. So they put this little bit of plastic on there to help keep it fresh until you're ready for it. But that's kind of a telltale sign when you're at the checkout next time. You can be like, oh, I remember that Zinc-Air battery.
In our research, we found that you can find these zinc batteries in hearing aids, headphones, and pacemakers. What makes their cell chemistry so useful for these small devices?
That's because Zinc-Air batteries are really good at delivering high energy density and lasting a long time for low currents. So for very small electronics, hearing aids, sensors, that kind of thing, they're very good. You mentioned pacemakers, which is actually not really a Zinc-Air battery technology, but a zinc mercuric oxide. When we think about zinc battery development, a lot of it really started during the Second World War, when the Army needed a lot of batteries that were sufficient to work in high humidity environments and combat situations. And this guy named Samuel Rubin developed a zinc mercuric oxide battery that the Army used a lot in the Second World War. And that went on to actually be the very first battery that was used to power a pacemaker. And eventually, that's been replaced by other chemistries that don't contain mercury. But you can still see it today if you're a Breaking Bad fan. You may know the scene where they're stuck in the desert and they have to make a battery out of, what they have on hand. And that's actually what they make. It's a zinc mercuric oxide battery using, galvanized nails and bits from the brake pads.
Yeah, Breaking Bad also taught me to be careful with chemists.
Uh-huh. Yeah. Never mind that barrel of hydrofluoric acid.
All right, Simon, let's draw a slightly bigger picture here at first. I know when we talk about disposable batteries, such as this one, we talk about zinc manganese oxide batteries, but this is not a Zinc-Air battery. Once more, how many different types of zinc batteries are disposable batteries and are rechargeable on the other hand?
It's an interesting point because you can actually combine very similar materials in different ways to build different batteries. Like the battery that you're holding up, alkaline zinc manganese dioxide, a lot of the materials in Zinc-Air batteries are actually the same. So we use zinc powder as the anode, and manganese dioxide can also be used as a oxygen reduction catalyst. So we see a lot of the same materials coming up time and time again. But over the history of the Zinc-Air battery, a lot of it started in the 1800s, early 1900s with zinc carbon batteries, which again, basically zinc and manganese dioxide, but originally using a chloride-based electrolyte, like ammonium chloride or zinc chloride. And there's another funny story that in the early 1960s, when zinc carbon batteries with these ammonium chloride electrolytes were like the big thing, There was a young engineer named Louis Urey who was working at, I think it was Everready. And he was given the assignment to try to extend the lifetime of those batteries. But he didn't really want to do that. He was more interested in working on alkaline electrolytes. And he got together with another guy working there named Carl Cordish, who is playing around with new binder materials. And they actually came up with that design for the battery that you held up just now. And the management didn't really want to hear it. So in order to make their case, yeah, exactly, they got one of their new alkaline batteries, and they got one of the old zinc carbon batteries, and they put them in two race cars and raced it through the cafeteria at lunchtime. And of course, the alkaline battery went forever, and the zinc carbon battery with the chloride electrolytes died pretty soon. And it's hard to argue with that. And yeah, the rest is history.
That is a great story. We're talking about the materials today, about zinc carbon batteries, about zinc manganese oxide batteries. But then again, we're talking about Zinc-Air batteries. Simon, at the very beginning, are these considered zinc-ion batteries?
No, short answer. So when we talk about Zinc-Air batteries, we're converting zinc on their anode into zinc oxide, and we're using oxygen from the surroundings to do that. Zinc-ion batteries have a fundamentally different mechanism. There we're actually dissolving zinc into our electrolyte and inserting it into an intercalation material, like, again, our old friend manganese dioxide, in much the same way as lithium-ion batteries do. The name zinc-ion battery it's a little bit misleading because typically, like, ion batteries use insertion on both sides, and here we're actually just dissolving and replating our zinc electrode. But yeah, it's a hot topic and one of the potentials for post-lithium-ion battery technology.
So we see that historically this technology is pretty old and it's been effective for a long time. You can do the race car comparison and the alkaline lasts forever. But now researchers are trying to make these very good batteries rechargeable, right? And that seems to be quite tricky. So how's that going? Can you give us a bit of an update on that research field?
It's probably good to start with the idea of, why is it hard to make them rechargeable in the first place? When we think about lithium-ion batteries and why are they so stable, we're not actually dissolving and replating anything. The material itself stays pretty much the same, and we're just sticking lithium into those free spaces. But zinc electrodes are fundamentally different. In zinc electrodes, you start off either with a powder or with a foil or with zinc metal in some form. And as the battery discharges, that metal is actually dissolving and going away and eventually coming back out as zinc oxide.
So you're kind of destroying the origin material, right? The zinc is kind of gone when the process is complete?
Exactly. And so you're dissolving it as it's discharging, and now when it comes time to charge it again, you have to replate that metallic zinc on something. But if all the zinc is gone, where do you replate it? And so you can think of it kind of like, maybe like building a Lego model. I can give you a Lego model and say, take it apart and build it back. And you might get it close, but it's probably not going to be exactly the same model that I gave you. And now you do that 100, 500, 1,000 times. By the end of it, you're going to get something completely different. And zinc electrodes are a lot like that.
We see in the lithium-ion technology, the lab cells accomplish more than 10,000 cycles. How does that look with Zinc-Air batteries? How many cycles do the latest lab cells accomplish? What's like the record?
The absolute best lab cells that you see published will typically be on the order of 1,000 cycles, maybe 1,500. Most will be on the order of a few hundred cycles. But that's kind of okay, because when we think about, what are the applications that these will be used for, we tend to look at lithium-ion batteries, and they're just great all around. They can do everything: high power, high energy, high cycle life. But, that's also kind of limited. We don't have infinite materials for lithium-ion batteries, but we do have a really big need for electrification. So the question becomes, how can we look at other applications like stationary energy storage or home energy storage, where safety is really important? And how can we get the cycle life of Zinc-Air batteries up to a point where it's good enough And we can still lean on those other really big advantages of Zinc-Air batteries, which are namely low cost and high safety.
Isn't also another advantage of these Zinc-Air batteries that they are that they have a very high voltage level or also very high energy density?
They have a very high energy density. And you can think about it as, in most batteries, you have two electrodes that contain all of the active material that you need for that cell to function. But in Zinc-Air batteries, it's pretty much mostly the zinc. And then you have a small gas diffusion electrode where you can, use the oxygen from the air. But most of the mass and most of the volume is just one electrode, where in most batteries you have two. So you can get very high energy density. Theoretically, it's like 6,000 watt hours per liter. In practice, you can get, I think 1,400 is like, these little button cells. Not a very high voltage, though. Lithium-ion batteries, they'll operate at, 4 volts, 3 volts, somewhere in that range. But because Zinc-Air batteries use a water-based electrolyte, which on the one hand is a big advantage for sustainability and safety, but because they use a water-based electrolyte, they're limited to the electrochemical stability of window of water, which is typically about 1.2 volts theoretically. It's an interesting point about Zinc-Air batteries, though, because the open circuit voltage on most practical cells will be about 1.4, 1.45 volts, which is bigger than 1.2. And so technically, the zinc electrode is actually unstable in water, thermodynamically unstable. It should evolve hydrogen gas. But through some kind of clever engineering ways, and because it's kinetically limited, we can make it practically stable, even though it should be unstable.
At this point, Simon, let's talk about materials. Could you describe briefly the structure of typical Zinc-Air batteries? I don't know if there is even a typical Zinc-Air battery. I think you just mentioned that on the cathode side, oxygen or air is reacting. Might be the reason why it's not meant for these pacemakers, since we don't have air inside of our bodies, correct?
Yeah, exactly. So we can think about it from that approach. Let's start on the air electrode side. So first and foremost, if we're using air from the surroundings, we need a way to get it into the battery. And so our air electrode is usually a porous structure that is coated with a oxygen reduction catalyst, in many cases manganese dioxide, that allows the oxygen to come into the battery and create an interface between our catalyst and our electrolyte. Now, the electrolyte is the part of the battery that's responsible for moving charge between the different electrodes. So our electrolyte is going to partially fill that kind of porous structure where our oxygen is coming into, and transport hydroxide ions from the positive electrode through the separator to our zinc electrode, which is basically a lump, but a lump of zinc paste. Which is many, many zinc particles that are all kind of interconnected and form a thick porous structure where those hydroxide ions will then react with zinc to form zincate and eventually precipitate out as zinc oxide.
So the zinc part is also a bit porous, like the air part is porous, you just said. So the zinc part is also a porous structure?
Exactly. And this kind of is the name of the game in batteries, is creating good interfaces. Because that's where the reactions are going to take place. So in many lab cells, you'll see that they'll use a zinc foil electrode, which is fine for doing evaluations and fundamental investigations of zinc electrodes. But in practice, you need a large electrode that has a lot of surface in order to get good energy density and to be able to make use of all that active material. So on the one hand, the air electrode is a kind of porous structure that allows air to come in and create a boundary with that electrolyte in there. And the zinc electrode is porous, that's just filled with electrolyte to try to make room for ions to move and to be able to access those interfaces where the reaction actually takes place.
And just for the record, what kind of materials are found in the electrolyte?
As we mentioned, it's an aqueous electrolyte, which means that water is the solvent. And that's really nice from a safety and sustainability perspective. And into that, we dissolve usually potassium hydroxide in very concentrated solutions. And sometimes you'll also mix in some additives like zinc oxide to try to get it to where it's actually already saturated with zinc. You can add in some other additives like potassium fluoride or some carbonates to try to extend the lifetime. But fundamentally, water and potassium hydroxide.
So I just have one follow-up question for the structure, because when you have this porous special structure designed for the zinc part, and then you just kind of take the whole structure apart because you're dissolving the zinc, how do you put that back together, right? A foil I could get that's just flat, but how do you get the same structure?
With great difficulty.
Okay.
That's a good answer. And it's also kind of worth thinking about, what is actually going on there and why is it so important that we have that porosity in the first place? And one of the interesting things and one of the challenges in Zinc-Air batteries is that when your zinc electrode is discharging, it's dissolving from metallic zinc to aqueous zinc species, and eventually it hits a saturation limit where it starts to precipitate out zinc oxide, which is your final discharge product. And that might be okay, except for two things. Number one, zinc oxide is about 60% bigger than zinc. So that means that as the cell discharges, its volume is going to want to expand. The second problem is that zinc oxide tends to precipitate onto those zinc surfaces where the reaction is taking place. And as that starts to get thicker and thicker and thicker, it's getting more and more difficult for those hydroxide ions to travel through and reach the surface. And eventually, once that gets so thick, it can't do it anymore. And you reach a state that's called passivation, where the zinc electrode just can't sustain any more current.
That sounds really difficult when talking about the cell formats and the cell sizes. Are Zinc-Air cells always bound to the coin cell format, or are they also possible in other, let's say, cylindrical or prismatic sizes? Is that volumetric change of the anode side a difficulty there?
Obviously, the most common format is the small coin cells. But if you want to get into like stationary storage or any kind of like really big application, then you're talking prismatic cells. And you do see a lot of prismatic cells for stationary energy storage. A lot of these companies that are pushing Zinc-Air batteries for industrial applications use the prismatic format. But you're right. As the size of the electrode gets bigger, the shape change challenge becomes more and more of an issue. And there's a few ways that we can start to deal with that. As I mentioned, one of the structures of zinc electrodes that we use in the disposable batteries is pretty much just a lump of zinc paste. So they take zinc powder, mix it up with a bit of electrolyte and binder, and kind of squeeze it into the case. But there are other ways to do it. You can center your zinc electrode so that instead of just kind of having loose particles all touching each other, it actually starts to create more of a foam, like a continuous foam structure of zinc. You can use another substrate like copper to plate on, so that even if all of the zinc is dissolved, you still have the same copper substrate there that can act as a base for replating your electrode. But it's a really interesting challenge and something that's, we don't encounter at all in lithium-ion batteries. So it's nice to have a new puzzle to solve.
Sounds really challenging, but exciting at the same point. We want to talk about scalability in production, about recycling, but we kind of forgot to talk about zinc itself. You said in the electrolyte there is some potassium, some carbon, manganese. That sounds really sustainable. We have never talked about zinc. How abundant is that element in general in the Earth crust?
Zinc is the 24th most abundant element in the Earth's crust. It's comparable to like nickel and copper, something like that. And one of the great things about zinc, as we kind of mentioned earlier, is that it's already used in a lot of industrial processes, galvanizing different metals. So there's a well-developed supply chain for mining it, for processing it, for recycling it. And it's also fairly cheap. I think the current prices per ton are about $2,600 compared to like $15,000 for nickel or $10,000 for copper.
Well, then let's talk about recycling. Is it actually easy to get zinc out of used batteries?
Yeah, so when you think about recycling lithium-ion batteries, for example, the materials there, you have a host structure and you're putting lithium into it, but you can't really just take it out and reuse it again somewhere else. You have to convert it back to its constituent materials and recreate it. But zinc is kind of different. There, you're just converting between zinc and zinc oxide, so it's a really easy conversion to make, and you can do that electrochemically in an efficient way. And that's why we see in some stationary configurations for Zinc-Air batteries, they'll actually do the recycling of the zinc right there in the container, where they take used zinc oxide that has come out of the battery, reconstitute it to zinc electrochemically outside, and then feed it back in to the battery later.
So is that a design that is used for stationary batteries? It sounds like something that could work there. I just pull out the used material, push in new stuff, and say, go.
Yeah, exactly. And stationary applications, I think, are one of the big markets for Zinc-Air batteries at the moment, and moving into the future.
That sounds very surprising, because when we did our research and we read about pacemakers, we were all talking about high density, very, very small batteries. And now you're saying, yeah, stationary, that's a good use case. Can you just elaborate on why that works for that technology as well?
Zinc-Air batteries have a couple of advantages that lead to different applications. And, typically we look at it and say, wow, high energy density, very safe. Let's put it in hearing aids. Let's put it in these things where we need really high energy density applications. But when we start looking into, as we mentioned, the cyclability, okay, we can get maybe a few hundred cycles reliably. And when we look at the power capabilities and the response, not so great for mobile applications like electric vehicles or those kinds of things. But that really does meet the needs of stationary applications, especially things like load shifting, where that you're going to need to move energy from, the day when you get solar energy to the night when you need it. And you can schedule this and keep it working at a kind of a constant baseline. And secondly, they are inherently safe. Which is these days you read, it seems like every few weeks in the news about some sort of fire happening somewhere. If that process were to occur in a Zinc-Air battery, where you get a dendrite forming and actually creating an internal short circuit in the battery won't work. That's about it. Like there's none of this thermal runaway issue. This is not going to catch on fire. So there's something to be said for using it in those applications where safety is very important.
But you also said that you have just about 100 or 1,000 cycles for these batteries. Now, if I buy a home storage and after 100 cycles it's dead, that's not really useful, right?
There's some kind of balance that has to be struck between trying to get the cycle life as long as we can possibly get it and trying to get the cost down as far as it can go. And that's, I think, one of the main selling points for Zinc-Air batteries is fundamentally that it's going to be a lower cost alternative to lithium-ion batteries. And that really has to be true, because if it's not, if you aren't able to get that cost competitiveness with lithium-ion batteries, then the argument for it becomes much more difficult. One important thing to also keep in mind about manufacturing is that Zinc-Air batteries are a lot more resilient to environmental changes in manufacturing than lithium-ion batteries. When you manufacture lithium-ion batteries, you often have to have a dry room that consumes a lot of energy. You're dealing with a lot of not nice materials. But zinc's not like that. Zinc is very stable. It's very safe. Lithium metal is kind of like a gremlin. If you get it wet, watch out. But zinc metal is not that way. It's much more resilient to changes in the atmosphere, much more resilient to humidity and exposure.
I have read something about Zinc-Air flow batteries, zinc hybrid cathode batteries, and as you just mentioned, they still have a problem with cycling more than 100 or 1,000 cycles. What do you think about the scalability of these battery parks made of zinc batteries? Is that going to work at the end?
Yeah, so if we think about approaching it from the perspective of how many cycles are really necessary, And let's take electric vehicles, for example, as a good kind of thought experiment. How many cycles do you think a electric vehicle needs to have in order to be useful?
I'd say probably 2,000 cycles.
Yeah, and that's a good guess. That's what a lot of people would say is, thousands of cycles, of course. But if we think about it and we say, okay, let's say that the range of the car is 500 kilometers. And if we cycle it 500 times, that's 250,000 kilometers already right there with 500 cycles. So we like to think that, thousands and thousands of cycles are a requirement for applications, when in many cases we can get by with a few hundred. Especially when that technology is cheaper and you can reduce the cost per cycle to a lower level.
So you're referring always to full cycles from 0% to 100% of charge.
You don't want to get into the question of what is a cycle with an electrochemist. that opens a whole can of worms. But yeah, generally from, let's say, 20 to 80%, kind of operating range.
I wanted to talk about the scalability in production with you. Now it sounds that it's just too small of an amount of Zinc-Air batteries that are produced nowadays. What do you think about the future? Are they good for production?
Yeah, so when we look at how did lithium-ion batteries get scaled up and what makes that so easy, and a lot of it is that you can do this roll-to-roll processing. It's very easy to scale up to large amounts, and it builds on technology that was mature, developed in other industries. When we look at Zinc-Air batteries, on the one hand, even though we can say, okay, it's not as widely used as lithium-ion batteries, but for the button cells, for example. There's factories in Germany, like Varta, for example, that have made billions of button cells for Zinc-Air batteries. So fundamentally, the technology can be scaled up to those levels. It's really just a question of how do you do it not only in high quantities, but supporting the large formats that you would need for larger electrodes for prismatic cells and these kinds of things.
Thank you very much for your time and expertise. That was Dr. Simon Clark from SINTEF. Dear audience, hit the subscribe button if you will. Do you think Zinc-Air batteries are the future? See you next time. Bye-bye.
Thanks for having me. Bye.